Hi, this is Roger from Kankan Labs, and today it's about improving the functionality of the sweep function of an analog function generator. And the improvement is this little circuit that I built over the last 2 weeks. Now, if you're watching my channel, you will already know this ELV function generator from one of the previous videos, where I also already showed you how to improve the functionality concerning the frequency counter with a reciprocal counter, which in the meantime I permanently fixed into this function generator. And you might notice some similarities between these two function generators. Well, this one here was sold as a kit as well as readily assembled. It must have been in the mid-90s. And this one here is the one I built from scratch for my home lab, which took some inspirations from the different iterations of this ELV one. But you already can see there are a lot more knobs at my one and some additional functionality. So before we come to the sweep function, let's take a broad overview, because today it's also about the usability and the ergonomics of analog test and measurement equipment. So first of all, both of them are based on the famous Maxim T8 function generator chip from Maxim. And sorrily, this chip is no longer available, as I once heard, I think it was in the Amp Hour podcast from David L. Jones and Chris Gamble. They once had a guest who told that, as far as I remember, the external chip factory where Maxim manufactured some of their chips burned down. And so all the masks of a lot of Maxim chips were destroyed. And that was the reason why for quite some time a lot of Maxim chips were not available, and they never resumed fabrication and producing new masks for the Maxim T8, but you still can get them at eBay and other sources. Why is this chip so famous about? Well, it goes up to 20 megahertz, and it's a much improved version of the old Interseal ICL 8038 or the comparable XR2206. And well, here at the ELV version, for example, one of the differences is here you control the wave shape with a push button, so it's controlled with flip-flops. And that's the first thing I don't like, because what I want are, as much as possible, switches and knobs, no push buttons. And the reason is simply you often have your eye on your test circuit, and when you have your finger on a switch, you always know at what position your switch is, while when you're using push buttons, well, you have to divert your eye from your test circuit and control at what setting your push button is. And the next thing is, let's turn it back to sine wave. The two waveforms are out of shape because I only can trigger on one of them, so the frequency is a little bit drifting at the second channel. And because they are analog, they don't have a quartz crystal controlled frequency. So the next thing is, and that is what I totally can't understand, the range switch. They have a 6-position range switch, and every range goes up by a factor of 100. Why is that? And then they only have a coarse and a fine potentiometer to set your frequency. And the coarse one is even not a logarithmic potentiometer, it's a linear one. What did I here do at my own home build? I have, first of all, a 10-turn potentiometer where you control your frequency really fine. And so I've retrofitted here the ELV1 with also a 10-turn knob, so you have a very fine control. You don't need anymore the fine control potentiometer, because the 10-turn pot is so exact in the setting that you can set it nearly to better than 3 decimal places, and more is not necessary simply because you have always the thermal drift. So the combination of a coarse and a fine potentiometer would be okay if the coarse one would have been a logarithmic one. And then the range switch, they wasted 2 of the position. You have a position 0 where the function generator is switched off. What's that for? And then in the highest range, they had an extra setting for the highest range from 10 to 20 megahertz. So totally unnecessary, just wasting 2 settings. And then the other settings go by a factor of 100. So for example, here you have a range from 1 kilohertz to 100 kilohertz, and the next is from 100 kilohertz to 10 megahertz. So what if you want to sweep, let's say from 50 kilohertz to 2 megahertz, then you are between the ranges. What I did, I made 6 ranges differing by a factor of 10, so that you are always combined with the 1 in 600 sweep ratio between the lowest and the highest settable frequency. You always find a range that fits to your desire. And next is, for example, for the DC offset, they also took a push button. I can't understand why they did this. Don't know, yeah, it's working now. So they could have done this simply with a simple switch. Well, push buttons are cheaper than switches, but saving some pennies just to make it look more professional and giving up the usability, I really can't understand it. But now comes the worst part. How to set the sweep function. Well, first of all, well, now it's turned off, you have to set the center frequency of your sweep range with your frequency control potentiometer. Then you have to turn it on, and now you have another push button setting to the minimum frequency of your range that you control with this potentiometer. And then when you finally turn on the sweep function, you're sweeping between the minimum and the mean plus the difference. So totally useless in my view how to operate with this. And again, for the sweep frequency, again, it goes from 1 hertz to 100 hertz. That is quite okay. I would have preferred going from 0.1 hertz to have a very slow sweep up to 10 hertz. But again, a linear potentiometer. So at the first quarter of a turn, you go from 1 hertz directly up to 25 hertz. So much too fast. Using a logarithmic potentiometer also, which would have cost perhaps €1 more, would have made this thing much more usable. So let's turn this stupid function off. How did I do it in my version? Well, first of all, you have an extra switch for turning the sweep function on and off. And then I have a 3-position switch. So you have 2 different 10-turn potentiometers. When you put the switch on the upper position, you're adjusting the high frequency limit of your sweep. And when you set it to the lower position, you control the low frequency end of your sweep range. And then when you put it in the middle, then it sweeps from the previously set minimum to maximum. And what was very important for me, having a switch to switch between linear and logarithmic sweep. So this is linear sweep, and this is only usable when your minimum and maximum sweep frequency are quite near to each other. But because you here have a sweep ratio of nearly 1 in 1000, you can sweep nearly the whole audio range, for example, from 20 Hz to 20 kHz. Let's try this. We are in the position 20 kHz. So let's set so the lowest possible frequency is 50 Hz. That's not 20 Hz. That's because the MAX038 does not exactly have 1 in 1000. I think it's 1 in 300 or 1 in 600. So we set this, we leave this at around 50 Hz and set the highest frequency range in our sweep to exactly 20 kHz, as good as possible with a 10-turn pot. So, and now you know this from your audio equipment, for example, when you see any diagrams with the frequency ranges, etc., they always have a logarithmic frequency scale, just because from 20 Hz to 20 kHz are 3 decades, and if you would scale this in a diagram linearly, you couldn't distinguish anything that's happening below 1 kHz, but if you scale it logarithmically, let's turn it on. So you can see, perhaps you can imagine that the frequency goes kind of 1 octave per, let's say, per second upward. And that's also how the human senses are working. Not only is the loudness that we perceive is in a logarithmic fashion, also the frequency that the human ear perceives. One step is like 1 octave, and the octave unit, also a factor of 2 for each octave, also is the logarithmic unit. And this shitty thing here only has linear sweep. So 3 things that are completely unusable. The awkward way how you set your minimum and maximum sweep frequency, the non-logarithmic way of your sweep frequency setting, and then that the sweep function is only sweeping linearly, while here you can switch between linear and logarithmic. You can see the difference in speed, how fast the frequency goes up in linear and compared to that in logarithmic mode. And because I wanted to make this thing just as usable as my home built one that exactly fits to my desires, I took the last 2 weekends not only to retrofit this with a reciprocal counter instead of the also unusable classical counter, I also rebuilt the circuit that I used here for the sweep generation, just in an improved version. And I would like just to know your verdict later if you think that it's worthwhile to make a Kickstarter campaign out of that. I don't know if I can find 50 people in the world who would buy this one. That's just the limit where it's worthwhile or where it pays off to make really the PCB, etc., and the layout for this. Now, it looks a little bit complicated, but if you look at the circuit diagram, it's not that complicated at all. The centerpiece is a little 80 mega 88, a small AVR controller. We have a voltage inverter, the classical ICL 7660, to generate from plus 12 volt power supply voltage, the minus 12 volt, which we later need for the op amps. And you have the control potentiometers. As you can see, I've one potentiometer for the sweep time, which by the software is scaled logarithmically. So here I can sweep from 100 Hertz up to 0.1 Hertz. And I have the same method of setting minimum and maximum frequency here with 10-turn potentiometers, and the switch which switches between setting the lower frequency, the higher frequency, and then sweeping. And here is the little switch for linear and logarithmic sweep. And basically that's all, but the difference is here I used as a kind of digital to analog converter, I used the PWM output and a very steep, I think, 8-pole filter, while here I used a modern digital to analog converter, the Max5136. It's a 16-bit converter with 2 outputs and an internal reference, so you need nearly no external circuitry. But what I've added is 2 little jumpers to make the output either unipolar or bipolar. So because there are some frequency generators where the sweep input needs a bipolar input, for example from -5 to +5 volt, and by setting or drawing the little jumper you can change between unipolar and bipolar output. And 2 little scale potentiometers. Well, and you can see we have 3 BNC outputs. One is the DEC output for the sweep frequency, then an X output if you want to use your oscilloscope in XY mode, or a sync pulse to start which is output when the sweep starts. And that's basically all. You need a 12-volt power supply, external, and that's all. So let's see how this thing works in practice. So first of all, let me demonstrate how the difference between the linear and the logarithmic sweep looks. This is the logarithmic function, and that's how it looks in linear mode. And of course also we can change the higher and lower frequency during the sweep. There's always a short interruption simply because the microcontroller recalculates the values. And now I'm setting down the higher frequency band or end of the sweep range. Let's put it back again to maximum. And if I increase the lower band, you can see that the curve is, or the start frequency, or the control voltage for the start frequency is going up. So in my view, quite nice. And also here, the 10-turn potentiometers are internally scaled logarithmically, so that you have an extremely fine control of your lower and your higher frequency start and stop frequency. So now let's connect this with a sweep generator and see what the output looks like. So let's check if it works. I've set the lower frequency to around 150 Hertz and the higher frequency end of the frequency range to around 15 kilohertz. And now let's start the sweep. And you can see it nicely sweeps here with a factor of 100 in logarithmic mode. Now, the XY mode with the Rigol is notoriously bad, so I've set it, or we will set it to trigger with a sync pulse, and the sweep time is 10 seconds. So let me change a bit. And so now I've set the horizontal time to 1 second per division and put the trigger point just to the left so that we have 12 seconds. And of course now you can only see just the peak level of our frequency, because the sine signal is of course compressed here totally. But now you can also do a little trick when you use the math function and set the y-axis to a logarithmic scale. You can already have a dB scale, and the upper part will give you your frequency response. So that's an easy way to measure the frequency response with your analog or digital oscilloscope, and only the digital ones can be scaled directly to dB. Now we of course have still a linear scale in the y-axis. So that was it for today. I hope you liked it, and please do me a favor. I will put a little questionnaire what you think about this thing, if this could be a commercial product for those few nerds out there which still have analog function generators and still need a good logarithmic and universal sweep generator for them. And well, thanks for watching. Until next time, bye from Roger, bye from Kanker Labs.